Hello, I'm Justin Pinkney and I'm going to talk to you about clip-to-latent, a method for creating text-to-image models from a pre-trained Stylegan using denoising diffusion and clip. This work done in collaboration with Chuan Li at Lambda Inc. So Stylegan is a well-known generative adversarial network architecture which can generate high-resolution, high-quality images of all sorts of domains. In particular, it's famous for generating high-resolution images of faces. Typically, these models are trained unconditionally, so we just draw random samples from a Gaussian distribution as the Z latent vector. We pass this through the Stylegan mapping network to generate intermediate latent vectors W, and from these latent vectors we can generate high-quality 1024 by 1024 images via the Stylegan synthesis network. So to add text-driven sampling of this pre-trained model without any modifications to the model itself, we want to be able to sample latent vectors based on some text input. And in order to do this, we're going to make use of another well-known pre-trained model called CLIP. So CLIP is a multimodal model for comparing images and text based on their similarity. It has an image encoder and a text encoder, and it encodes both into a shared latent space in which they can be compared for similarity. So once we've generated a bunch of Stylegan images based on some latent vectors, we can pass these through the clip image encoder to get the corresponding clip image embeddings. Now we've got pairs of Stylegan latents and clip image embeddings, and we can match up these two latent spaces by using another model. So we're going to train a denoising diffusion model, which we term clip-to-latent, to generate W vectors, so latent vectors for Stylegan, based on the image encoding provided by clip. So we can train this very efficiently using only synthetic data generated by Stylegan encoded by clip. We also do a couple of other tricks. So for example, we add some noise to the clip image embeddings, which is going to help it to generalize not just to images but also to text even better. And at inference time, we rely on the fact that clip has this image and text shared embedding space. So we can, instead of putting in an image, put in a short text phrase, so middle-aged man with a moustache and a happy expression. We can generate the text embedding for this rather than the image embedding. Then we use that as the condition for our clip-to-latent denoising diffusion model in order to generate latent vectors. We can then pass these latent vectors to Stylegan, the synthesis part of the network, and generate high-resolution images from these latent vectors. And you can see that this well matches the output, the text prompt that we gave it. So here are some examples of a couple of trained models. On the top row, this model was trained with the well-known Stylegan 2 pre-trained on FFHQ. You can see the text prompts at the top, and underneath the corresponding images generated by the Stylegan latents. So you can see that they match the text prompts pretty well, and they are high resolution. They're 1024 by 1024 pixels, and are generally quite high quality. Clearly, these are still restricted to lie within the domain of the pre-trained Stylegan, so they're all photographic images of faces, all aligned to the particular dataset on which it was trained. But you can also see that this generalizes to other architectures. So at the bottom, we have a row generated by this alias-free version of Stylegan, termed Stylegan 3. This was trained on a dataset called LHQ and was trained at a resolution of 256 by 256. So again, you can see the text prompts at the bottom and the corresponding images generated by the latents that we sample using clip-to-latent. To compare our method to some other text-to-image approaches, we generate some samples using clip-to-latent, and you can see the results in this row. So these vary from straightforward descriptions of people to things which are harder for the model to interpret. So on the right, there are descriptions of non-photographic characters, so from animations, and you can see that because we're constrained to the domain of Stylegan, we generate realistic human faces of those, although they inherit many of the characteristics of the original cartoon characters from which we requested. We can compare our method to direct optimization of the Stylegan latent vectors based on clip. So here we sample a random latent vector, we pass it through the Stylegan synthesis network, we generate an image, encode that with clip, and use clip to measure the similarity of that to a text prompt that we want. We then use backpropagation in order to tell how we should adjust the latents, and we do that in an iterative fashion. To do this method, we call direct optimization. As you can see, this, as is known, produces images which well match the prompt. However, you can see that there are many more artifacts introduced because the latents generated tend to be pushed outside of the typical domain of Stylegan. Another method we can compare against, which is again trained without any text label data, is called Lafitte. So this is a pre-trained model from the original authors of Lafitte, and although it's trained on a slightly different data set, it allows us to sample faces with the same alignment using the text prompts provided. You can see that the match to the prompts is reduced and the overall fidelity of the images is lower, and also these pre-trained models are generated at 256 by 256 pixels rather than our 1024 resolution. Finally, we compare to a state-of-the-art text-to-image generation model, namely DALL-E 2 from OpenAI, which we use via the DALL-E 2 API. You can see that although the images are very high quality and the same resolution as ours, and they tend to match the text prompts quite well, they don't have the same alignment and structure as our images, so they're harder to compare. So we can add some prompt engineering in order to try and produce photographic aligned images of faces, for example, for producing headshots from text labels, and we can get a lot closer to a comparison of our to our method. However, despite much effort in prompt engineering, it's not always straightforward to generate realistic images of faces, as can be seen from Chihiro and Eric Carbon, who are still non-human characters. Finally, because we're using the pre-trained Stylegan without any modification, we're just developing a new method for sampling it, we can then use all the well-known tricks for modifying images based on Stylegan that's been developed in the extensive Stylegan literature. So we can use truncation to reduce artifacts if we notice distortions or other artifacts in our images. We can use style mixing, where we change the latent code for the high-resolution part layers of the Stylegan network. This allows us to introduce variations in terms of lighting, colors, and textures to an existing latent that we've sampled from a text prompt. And finally, we can use all the well-known Stylegan editing methods in order to change our generated image. So on the right, you can see a generation for an Arctic explorer, where we've applied edits for age, pose, and smile presented in the interface scan paper, and you can see these are represented well in the final outputs. This is an important point because editing will not necessarily work smoothly. It's been shown that if latents lie outside of the typical domain of Stylegan, your ability to edit is compromised. And this is shown in this sample, where on the top row we have the example I showed before, where we edit a clip to latent generated latent using well-known edit directions. And on the bottom, we take the same prompt, use the direct optimization approach in order to generate a sample, and then we further edit that sample. And you can see, because that sample doesn't lie well within the Stylegan latent space, it tends to generate artifacts and corruptions, ending up on the far right with a complete loss of the original face. So in summary, we've discussed clip to latent, a method for adding text-based sampling to any pre-trained Stylegan. It's data efficient because it doesn't require any external label data. That's all generated from the GAN itself. It's compute efficient because it trains in a few hours on a single GPU, and at inference time, using tricks like time-step respacing, we can generate images with times much less than 1 second per image, and we get output resolutions of 1024 by 1024 pixels, the native resolution of the pre-trained Stylegan. So I hope you enjoyed the talk. You can find all of the code and the pre-trained models at the GitHub URL listed at the bottom. And if you want to try out the models yourself, you can do so on Hugging Face Spaces. Just search for Clip to Latent Demo on Hugging Face Spaces, or navigate to the URL, or scan the QR code to get taken directly there. So I hope you enjoyed the talk, and thank you very much for your attention.